Uh, Hello, everyone. Welcome to another lecture of Deep Learning Theory and Data Science. In today's lecture, we're going to talk about discriminant analysis, linear and quadratic discriminant analysis. So first of all, let's begin with a meme that I think is important to understand today's lecture. In this meme, you see a person whose job is a data scientist. And this person is facing a challenge. The challenge is an unknown distribution. And what this person does is he's trying to overcome the challenge by, sticking this thing. And essentially the joke is that a data scientist is always trying to fix everything using the Gaussian distribution. So maybe at this point it doesn't make sense, but hopefully by the end of the lecture this meme makes sense. And in today's lecture we're going to talk about an algorithm that was originally proposed by Sir Ronald Aylmer Fisher, who goes by the name of R.A. Fisher. And here you can see a picture of him on the right, and on the left, you can see some quotes describing this person. So these are quotes from Wikipedia. And they say a genius, so for his work in statistics, he has been described as a genius who almost single-handedly created the foundations for modern statistical science. And he was also called the single most important figure in the 20th century statistics. Important person. And I would welcome you to read the Wikipedia page. There's other things that are a bit controversial about R.A. Fisher that I prefer not to talk about during the lecture, but maybe you should read on your own. And one of the things that Fisher has done was Fisher was one of the first people who were doing classification. And is he the Fisher information person? Yes. So back in the day, people didn't have ImageNet, didn't have CIFAR, they didn't have MNIST. What they had was something called the iris flower dataset. So the iris flower dataset was used by Fisher in his original works that were introducing the algorithms that we're going to discuss today. And essentially this algorithm, this iris dataset is a dataset of flowers. So the features are related to the petal and the sepal. I actually don't know what's a petal and a sepal, but I assume some of you know. I think petal is like a part of a flower and sepal is another part. And you can see how the petal and the sepal, I'm not even sure if I'm pronouncing this correctly, have a height and a width, right? Height and a width. And so the features in this data set are the sepal length and the sepal width and the petal length and the petal width. And the class is the type of flower, right? So this is the data set that Fisher had at his disposal. And what Fisher was interested in doing was classifying these, data and determining what kind of flower, is at hand based on these features. Okay, nice data set of flowers. Do you like flowers? I love flowers. Okay, now, if you remember, the sticker beforehand said that a data science is always sticking a Gaussian distribution on everything, right? So there's, in Fisher's classification, he relied on a generative model, which is called quadratic discriminant analysis. In this generative model, one assumes that the distribution of the sample X given the class C is Gaussian, right? So this is a probability density function of a multivariate Gaussian. Do you recognize the Gaussian here? Have you seen Gaussians in your professional or non-professional life? A little bit, okay. Now, let me just say that the PDF of a Gaussian, just think of it as some ugly constant that you don't care about and you can ignore for the most part, multiplied by exponent of some quadratic function. This is a function that's quadratic in the X, right? So this is like a second degree polynomial. Now, in addition to this assumption, so you see this is a very strong assumption about your data, right? Because you're assuming that your data is Gaussian, right? So you understand this picture here? Gaussian. And the other thing that we're assuming is that the probability of a certain class is this small pi c, okay? So for example, if you have 5 classes and all the classes have equal probability, pi c is 0.2. Now, given this generative model, how can we classify a new data point? So if I give you a new data point X, how would you classify it? You would try to look at what's the probability of each one of the classes given the current data point, right? This is conditional probability. And you would just look for the C, for the class that maximizes this. Does this look sensible to you? What is the class that is most likely given the data? Now, notice that this probability can be rewritten as follows. Does anyone know what's happening in this Bayes? Yes, this is indeed Bayes' rule. Luke said immediately and correctly. And notice that in this expression, there is a thing which is redundant for the classification prediction, and that is the probability of the X. Because if I give you a certain fixed X and you try to predict its class, it doesn't matter what is the probability of X, right? It's just something that does not depend on C. So we can just ignore it, right? Just remove it. Moreover, notice that the argmax of a function is equivalent to the argmax of a log of a function. So we can just apply log. So we get log probability of y. Oh, sorry, I think there is a small mistake here. Let me fix this. This should be the log probability of x equal x given y equal to y, plus the log probability of the y equal to c, right? So this thing is the log of this thing, and this thing is just this thing, okay? Now, at this point, notice that we can just plug in the assumption that we have about the probability of x given y, right? And if we do that, we get this thing, Notice that certain terms disappeared. For example, what did disappear? This thing disappeared, right? So this thing vanished. Why did it vanish? Because it doesn't affect the argmax. This thing is just a constant, which is the same for all classes. So it does not affect your prediction, right? And notice that here we are assuming that, so this is the covariance of your data, right? And notice there is a subscript C. The subscript C implies that each class has a different covariance. Notice that here you have the mean, and notice that the mean has a subscript C. This means that each class has a different mean, a different class mean. Does this make sense? So maybe in short, you could write, x given y is distributed normal with mu c and sigma c. Maybe I should have written this. Now, at this point, we've obtained that this is the rule for classification. And if you were to massage this expression, then you would be able to show that the decision boundaries between the classes are quadratic functions, polynomials of degree 2. So here is an example of how this looks like in practice. So what we see here are two classes, the red class and the blue class. And what you can see is a bunch of dots. What are these dots? These dots are samples from our distribution. And you can see how, based on these samples, someone here is showing you the level sets of the Gaussian PDF, right? Probability density function. And most importantly, you can see how there is a separating, there is a decision boundary, right? And okay, so does anyone have any questions about quadratic discriminant analysis? No questions. Now, notice that in this slide, we're using quantities which are called in statistics population quantities. Why are they called population quantities? Because they're quantities representing the population. This should be contrasted with empirically estimated quantities. What do I mean by that? In reality, you don't actually have access to mu c or sigma c or pi c, right? Because in reality, you don't actually have the true underlying parameters of the model. So in reality, what you have to do is you have to collect data from this distribution, and then you have to estimate an empirical class mean. Notice the hat. Whenever you have a hat, it means empirically estimated. And you also have to estimate empirically the within class covariance, right? So what's written here, this expression is saying, take all of the xi's which satisfy that their label is the cth class and just average them. And that gives you an empirical mean. Have you seen empirical estimators in your life? No? Do the words make sense? No. Okay. A little bit makes sense. Okay. And here you can see the within class covariance, which is as well estimated empirically. So what we're doing, we're just averaging over xi's, which belong to class C, and we're just subtracting the class mean and calculating an outer product, right? And similarly, we can estimate the empirical class probabilities. So in this case, this expression is just equal to the number of examples which belong to the cth class divided by the total number of examples. Make sense? Now, in reality, usually it's rather hard to estimate the covariances for each class independently, because you have a very limited amount of data, and estimating a covariance takes a lot of data. So in reality, it is beneficial to use a single covariance matrix for all the classes. So usually this is called homoscedasticity. I'm probably mispronouncing that. And the homoscedasticity assumption is saying that the class have independent within class covariance sigma W. W is within. Okay. Now, this is equivalent to assuming that your generative model is the probability of the example given the class is this thing that we've seen previously, except now you can see here the within class covariance, which does not depend on the class, right? Now, at this point, you might ask yourself, how does the classification decision boundary look like in the case of, of this homoscedasticity assumption? So let's check it out. So first of all, notice that now all of these quantities are equal for all the classes, right? And so this thing does not appear once you look at the argmax. So if you're looking at the most probable class, this quantity is no longer relevant. Previously, it was relevant, right? Where is it? You see here, previously we had this log determinant, but now we don't have. The second thing that you should notice is, notice that you can subtract and add here from X and mu C, mu G. Mu G is the global mean. What is the global mean? It's just the average of all your data, okay? Why do I want to do that? Because I usually like to think about my data globally centered, okay? Zero mean. So overall, the data is globally centered, but you have different class means. Now, notice that argmax of this whole expression is equivalent to this argmax. So what have I done here? I've taken this X minus mu G and multiplied it by X. That gives us this quantity. And the second quantity that we have here is mu C minus mu G multiplied by this quantity, I believe. Oh, sorry, this quantity. And the third quantity, this thing, is what you obtain if you multiply, I guess, the remaining terms. So if you work it out, you can see that these are equivalent. But what's important to notice here is that if you massage this expression, you end up getting the following thing. You end up getting X, which is your input, signal, image, data point, multiplied by a certain vector, which is your classifier. And you also have an intercept or a bias, which is shifting your prediction. So what does this mean in simple words? What am I trying to convey by showing you this? It is a line, exactly. So the prediction is just a line. So the classifier is a linear classifier, okay? So if you remember last lecture, so we started this course by talking about deep networks, right? Deep networks are multi-layer nonlinear classifiers. That's 2020 or 21 at this point. Then we went back and we went to 1940s and we talked about logistic regression. And now I'm taking us even backwards to 1930s, and we're talking about linear discriminant analysis. We're part of a time traveling course, you see. Now, were you lured into a deep learning course, but in reality, this is a course about algorithms from the 1930s? Or is there actual, is there a point to all of this? So there is a point to all of this. Everything will come together soon, okay? So at this point, it should be clear that why is this algorithm called linear discriminant analysis? It's called linear discriminant analysis because the classification is linear, right? And this classification is different than logistic regression, and it's different than the max margin classifier that we've seen in the previous lecture, right? You can have a bunch of linear classifiers which are different. Now, notice that if you look at this quantity, then the classifier decision, if pi c are equal, so if the probabilities of all class are equal, the classifier decision is equivalent to choosing the nearest class center. What does that mean? It means that the prediction of the classifier is equivalent to taking x and then subtracting the class mean, multiplying by sigma w to the minus half, and minimizing the L to norm. So you're just looking for the closest class. And I'll have some illustration of this in a moment, okay? So here's the illustration. So first of all, what are we assuming in linear discriminant analysis? We're assuming that x given y is distributed as a normal distribution with a mean. Does anyone know what is the mean and covariance? No, not year one, not yet, not yet. So if you look at the previous slide, you can see that the mean is mu c and the covariance is sigma w, right? Make sense or does not make sense? It does make sense. Okay, so makes sense. Okay, so it's normal with mu c and sigma w, right? Now, because sigma w does not depend on the class, you can see how sigma w is the same for all the different Gaussians that we have. Does anyone know how is this type of distribution called? It has a well-known name. How would you call such a distribution? Gaussian mixture model, exactly. This is called Gaussian mixture model, or in short, GMM. Now, notice that here we have the different class means. So you have mu1, you have mu2, and then you have mu3, right? And around each class mean, we have its corresponding to covariance, right? You can think of this as the level set of one standard deviation away from the mean, if those words make sense. If those words make no sense, you can think of this as just a representative of the shape of the covariance, right? And you can see again how the covariance is the same for all the classes. Now imagine you transform everything by multiplying it by sigma to the minus half, right? That's what is written here. As a result, your class means become sigma w to minus half multiplied by mu1, sigma w to minus half multiplied by mu2, and so on, right? So how would you call it, this procedure? This procedure, I guess, I don't know if it's a bit politically incorrect, but back in the day, this was called whitening. But I guess you can also call it sphering, because it makes the distribution spherical, right? Now, after you transform your your mu's to sigma minus half x and your data point x to sigma minus half x, now if I give you a certain point, how do you decide what is its corresponding class? How do you do that? Notice that the noise here is isotropic, right? Isotropic noise means that it's spherical. The variance in all directions is equal. Yeah, so Kevin says, you just pick, given a certain point, which mean is it closest to, right? That's why it's called nearest class mean. okay? Now, at this point, you might ask yourself, what is the classifier, right? Can we represent somehow intuitively the classifier? So the classifier for the Sith class is simply looking at this vector, which connects the global mean, which is the average of all the class means, right? This is the global mean, and you connect it with the class mean. Does this make sense? So it's mu1, which is the class mean of the first class, minus the global mean multiplied by sigma within to the minus half, right? If you look a couple of slides beforehand, notice how here we had mu c minus mu g multiplied by sigma to the minus 1 multiplied by x, right? So the linear classifiers are of this form. And so here you can see the same type of form. Oops, here. Does this make sense? Does anyone have any questions? How many of you have seen linear discriminant analysis and know everything I've said until this point? No one? Okay, there's one person. Let's see, maybe there's more. Oh, one person. Okay. I'm sorry for the one person who has to suffer listening to my voice, which conveys no new knowledge. But I feel like we must cover, background material. Otherwise, the course becomes not comprehensible. Okay. So at this point, you can see that the classifier is just connecting the class means and the global mean, right? And if you go back to the original coordinates where the within class covariance is not spherical, then the classifier is just sigma w2 minus 1 multiplied by the class mean minus the global mean. Now, let's consider a specific case where we only have two classes. In this case, the global mean is going to be somewhere here, right? This is the global mean, mu g, multiplied by sigma w minus half. And the classifier is basically sigma w minus half, mu1 minus mu2, which is proportional to sigma w minus half multiplied by mu1 minus mu g. They're basically the same direction, right? So in general, the classifier is of the shape mu1 minus mu g. So you subtract the class mean from the global mean. But in the special case of only two classes, the classifier is equivalent to mu1 minus mu2. So it's just the difference between the classes, right? Now, what would happen? Where does the bias come into play here? Does anyone have any idea? So the bias would basically dictate where exactly is the cutoff beyond which you would assign something to class 1 or class 2. So for example, if you have a hyperplane here, right, or a hyperplane here, that would depend on the bias. It just dictates where this hyperplane is. So at this point, notice that in the linear discriminant case, you also have to estimate these, class means and within class covariance and so on empirically, because you don't have access to the population quantities, right? So you need to estimate empirically the class means, the global mean, the within class covariance, and so on. Now, you might ask yourself, what exactly is the linear discriminant analysis minimizing? Is there some objective? Is there some intuition beyond just saying, it's the, previously what we've said is that it's the maximum over C of the probability of y equal to y given x equal to x. But is there any other reason for why you would choose this linear discriminant analysis? So in this slide, I'm showing you a different perspective that also leads to a linear discriminant analysis. Okay. So imagine that you have two Gaussian distributions. And imagine I ask you to find a classifier that would classify them well. How would you choose a good classifier? So what you could do is you could try and think what would happen if I chose a certain classifier W, right? This is an example of a classifier you could choose. So if you choose this classifier, then all of these blue data points are going to be projected onto the classifier, right? Now, when they're projected onto the classifier, you get a certain mean, right? So if you project Gaussian data onto a certain direction, it remains Gaussian distributed, normally distributed. It's just that here it was, high dimensional distribution, in this case, two-dimensional distribution. But once you project it onto a classifier, it becomes a one-dimensional normal distribution, right? Now, what is the mean of this normal distribution? Here you can see the normal distribution, the one-dimensional one. What would be the mean of this normal distribution? So if basically what I'm wondering is if I take, yes, exactly, yes. So in simpler words, if this thing has a mean of mu1, what would be the mean of this one-dimensional distribution? Mm-hmm. Mm-hmm. Yes, W transpose mu1. Thank you very much. So this would have a mean of W transpose mu1, right? Which is a scalar because this is a one-dimensional distribution. And what would be the mean of the second cluster? So here we have a mean mu1. So mu1 is in R2. Sorry, this would be mu2, my bad. Mu2. Yes. So what would be the mean of the other thing? It would be the same. So it would be W transpose mu2, right? And so what's the difference? What is the difference between the two means? What is this vector here? Maybe I should use more bright color. What is this vector? This vector is simply equal to W transpose mu1 minus mu2, right? So this is one fundamental quantity because it measures the distance between the classes after they're projected onto a line, right? Don't you feel like this is a fundamental quantity? It is. Now, what is the other fundamental quantity that we care about? Since this is a Gaussian distribution, what do we care about except the mean? The variance, right? Yeah, but in this case, it's not a covariance, it's rather a variance because we're talking about a one-dimensional distribution, right? So what would be the covariance of the let's say of the class 1 after you project it onto the classifier? I'm not sure I understand if you're thinking if this is trivial or if you've lost me. I'm getting a mixture of both of those, all of those emotions. So maybe I can write it in a simple equation, just a very simple equation. W transpose multiplied by X, and assume that X has a class, 1. So let's say X, is in class 1, right? Then this thing would be distributed as a normal with a mean W transpose mu1 and a variance of W transpose multiplied by the original variance, which is sigma W, multiplied by W, right? So this is just a theorem that says, you know, how does the distribution of a Gaussian change if you multiply, if you apply linear transformation. And so this is what's written here, you see, W transpose sigma W, right? So what in simple words, what does this quantity measure? This quantity measures the width of the Gaussian, right? So we have two fundamental quantities here. We have the distance between the means and the width of the Gaussian, right? So what would be, you know, if you were tasked to find a good classifier, what would you do? So if you were Fisher, what you would do is you would try to maximize the difference between the means, right? While minimizing the variance, right? And so because you have two quantities, you just divide them. Why do you divide them? Because this quantity by itself doesn't make any sense, right? This is just a difference between two quantities. But what you want to do is you want to normalize it by the variance. And then you get, you know, a pure number, so to speak, right? So the ratio is extremely important. Not the one of the quantities by itself is not important. Now, if you were a, you know, double E person, and there's double E people here, they would usually call this the signal to noise ratio for a binary classification problem. Why is this a signal to noise ratio? Because essentially, you know, there's in life, there is good and there is evil, right? There's yin and there is yang. Actually, I'm not sure what yin and yang means, so maybe you should ignore that. But good, evil, signal, noise, dark and light, right? And so in this case, there's mean and variance. The mean is good because the more mean you have, right, the bigger the difference between the means, the better you are in classifying. Whereas the variance is hindering you, right? And so, you know, the difference between the means would be called a signal and the variance would be called noise. And what you're trying to do is optimize the signal to noise ratio. Now, one can show that if you optimize this quantity, then the optimal classifier has this form, right? Do you recognize this form? Have you seen this form ever before in your life? Maybe today. So this form is the classifier that we've seen for linear discriminant analysis. So if you see here, right, the classifier is just connecting the two class means after you transfer them by sigma W to minus half, right? So the classifier for linear discriminant analysis is sigma W minus half multiplied by mu1 minus mu2. And you can think of this classifier as just maximizing the signal to noise ratio written here. Why do people like, you know, saying that a classifier maximizes a certain objective? The same reason that people want to have objective in life, right? People want to have purpose, and people also want to assign purpose to algorithms. In this case, the purpose of an algorithm is to optimize the SNR, right? Now, how does one prove that? It's rather simple. all you have to do is just derive this quantity right here with respect to the classifier W. Okay, so all you have to do is derive it with respect to the classifier W. So let me show you briefly how it looks like. So first of all, we are interested in deriving the objective with respect to W. So let us write here the objective. The objective is this quantity, which is the mean squared, divided by the variance, right? Now, by the way, why are we squaring the mean? Does anyone know? Why do you square the mean? What's a simple intuition for squaring the mean? So have a kind of a hand wavy non-negative. Yes. Yeah, exactly, Jim Show. Variance squares stuff and mean averages stuff. So if you think about it in terms of, units, then variance has something like centimeters squared or inches squared, whereas the mean would be just inches, right? So you want to make them the same type of, this is such a horrible motivation, but this is my motivation and I stick to it. Now, at this point, we want to derive this quantity, right? So how do you derive this quantity? This is the usual derivative of a ratio. So you just copy the bottom and derive the top minus derivative of the bottom multiplied by, minus the bottom squared multiplied by the derivative of the top. So this is just the derivative of a ratio. At this point, what happens here is that this derivative is just equal to this thing. Why? Because this thing is equal to W transpose mu1 minus mu2 multiplied by mu1 minus mu2 transpose multiplied by W, right? Gina is asking, wouldn't it be divided by the bottom squared? Bottom squared. Bottom squared. Bottom squared. Oh yeah, it's possible that I might have skipped a step. Thank you, Kevin, for helping me. So notice that this quantity here is equal to the, oh, now I understand the question. Yes, 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 yes. So this quantity here is equal to this thing, right? Now, how does one derive this expression? Just by removing one of the W's, right? So that's what happened here. Just remove one of the W's. And then here we have similarly a simple derivative. How does one derive this quantity? Just by right, so here this is the quantity after the derivative. This other W, let me use a different color. This thing with the squared is equal to this thing, okay? So just simple, very simple derivatives. Now, at this point, notice that you can just divide by a scalar and equate to 0. So I'm going to divide by W transpose sigma W multiplied by W. And as a result, this disappears. And here you get divided by W transpose sigma W, W, right? Just division by a scalar. Now, notice that this quantity right here is by definition equal to J, right? This is just the definition of J. Therefore, what we obtain is a simple equation, which is, let me add here one extra step, mu1 minus mu2 multiplied by mu1 minus mu2 transpose multiplied by W equal to JW multiplied by sigma W multiplied by W. You know, it looks very horrible when I have sigma WW because it's extremely confusing, but this sigma W is sigma within, and this W is a vector, right? It just looks horrible because this looks like another vector, but it's not. It's there just to confuse you. Now, notice that this thing, you can multiply by sigma w to the minus half on the left. And after you do that, you get your sigma w to the minus half. And here you remain with sigma w to the half, right? At this point, we're going to do a change of variables, and we're going to call sigma w half w. We're just going to call it u, okay? Why do we do that? Because now we have what? What is this thing? Does anyone recognize what this equation is? Does this look like something you might have seen in your previous life? Something that you have learned to love and cherish? Something that you've seen maybe long ago? No. So eigenvalue, yes, thank you, Jack. So notice that this is just an eigenvalue equation. So you have a matrix multiplied by a vector equal to a scalar multiplied by a vector, right? Now, moreover, this is a trivial eigenvalue problem. Why is this a trivial eigenvalue problem? What is trivial about this? Why is this trivial? I don't want to insult the problem, but there's something simple about it. So think about the rank. What is the rank of this thing? What is the rank of the matrix? It is symmetric, that is correct. That is correct. That's part of why it's simple. But also notice that the rank of this matrix is 1, Tristan said with exclamation mark. That is correct. Now, why does a rank 1 matrix in the middle? So if you have a rank 1 matrix here, it implies that the whole thing is a rank 1 matrix. There's a theorem that maybe you've seen somewhere in linear algebra. And moreover, notice that the eigenvalue problem of a rank 1 matrix is trivial because it's basically equivalent to saying if I have VV transpose equal to, multiplied by U equal to lambda U. What is the eigenvector? The eigenvector is just proportional to V, right? So if you have a rank 1 matrix, the eigenvector is just the vector that creates the rank 1 matrix. And so based on that, you can conclude that the eigenvector U is equal to sigma W minus half multiplied by the difference of the means. So basically, here you have a vector, here you have the same vector transpose, right? And here you can see the same vector again. Now, why is it equality and not proportional? I leave you to convince yourself. And finally, the last step is because U was defined to be sigma W half multiplied by W, you conclude that W is equal to this expression, right? So that's QED, and that's what we wanted to prove, that the optimal classifier is sigma W minus half multiplied by the difference of the means. Okay. So it seems like we're out of time, so I will continue next time. Thank you for joining, and I will stay for questions. Let's look at the meme a bit more. I like it. Look at this. Is there an objective to optimize in the case of quadratic discriminant analysis? In the case of quadratic discriminant analysis, let me see. not that I can think of from the top of my head, Jack. Cannot think of one from the top of my head. You too. We do, Emily, and use those classifier rather than minimizing for some objective. Yes, yes. The reason I showed the objective for the linear discriminant analysis is that I'm later going to show the same thing for multiclass. And in multiclass, we'll see there's something extremely important. So my goal is to show the objective of multiclass linear discriminant analysis, because that would be useful for following lectures. If that makes sense.